lab write-up number 9, I'm doing the rotation of a pulley. Okay, so first off, the purpose of this lab is to understand how rotational momentum affects a pulley system, and to know the difference between the Atwood machine analysis and rotation motion when calculating the acceleration of a pulley with two different masses. Okay, so let's read the problem. Getting water from a well, we use a pulley, bucket, and muscle, or balancing mass. Let's say we have a pulley of radius r, and the moment of inertia of IA is hanging from a tree branch. We have a low mass and non-stretching rope attached to the bucket of mass 1, and on the other end to a counterbalancing of mass 2. Find the acceleration of the system if the two masses are different. So the first thing that we do, we're going to draw a diagram. And that's what I have here. I have the free body diagram on the left. And we can see here that mass 1 weighs more than mass 2 because the direction is clockwise. Okay, so the first thing that we're going to do for this problem is we're going to consider the sum of the forces. Okay, and then with the sum of the forces, okay, in 1, we have tension 1, okay, and that's and then we subtract mass 1 times g. Now that's the same as Fg that I have shown at the bottom. Okay, and then we're going to consider tension 2. Okay, now tension 2 minus mass 2 times gravity. Okay, now you can see that both of them end up being m, the mass times acceleration. Okay, well, one of them we need to make negative, so I just made this one negative. Now, what's next? Well, we need to figure out the sum of the torques. And I have that written, and I have this shown in the diagram below, that the tensions 1 and 2 are going straight down, just like the force of gravity. Okay, so we need to make up an equation. Well, first we need to understand what the torque is. Okay, torque is just the radius times the force times the sine of an angle, which is equal to the moment of inertia and alpha. Okay, we use alpha for acceleration. Now, we're not given any of the rotational motion characters. Okay, that makes sense. So we need to change our angular to linear. So we've got alpha equals acceleration times radius. Okay, well, we've got acceleration and we have radius. Okay, so now we need to figure out the moment of inertia. Well, when considering the moment of inertia, we need to factor in the shape of the object that we're using. Okay, and the shape here, the shape of a pulley, is a rotating disc. So we have a special equation that's just for that. Each shape has a different type of moment of inertia equation. And for a rotating disc, we have the inertia is equal to 1/2 times the mass and the radius squared. Okay, so now we can do the sum of the torques. Okay, so tension 2 multiplied by the radius minus tension 1 multiplied by the radius. Okay, now 2 um, I'm sorry. Okay, so moving on. So these must equal inertia times alpha. Now, this is negative. The torque is negative because the pulley is moving in clockwise direction. Okay, it would be positive if it was moving counterclockwise, but it's moving clockwise, so it's negative. Okay, so inertia. Okay, here's our inertia equation. And then for alpha, we just plugged in A over R. Now, we need to add the forces and the torques because we still need to find the acceleration. So we've got tension 1 minus mass 1 times gravity, which equals m1 times acceleration. Okay, and mass 2 times gravity minus tension 2 is equal to mass 2 times acceleration. And now we've got the sum of the torques. Okay, so tension 2 times the radius minus tension 1 times the radius is equal to negative 1/2 the acceleration times the mass times the radius. Okay, so I canceled out 1 of the radius because we had an r as a fraction. So there you go. Now what do we do next? We add them up. Okay, so we're left with the mass 2 times gravity minus mass 1 times gravity is equal to mass 1 times the acceleration plus mass 2 times the acceleration minus 1/2 times the mass and acceleration. Okay, so what are we looking for? Well, we need to solve for acceleration. And my face is going to be in the way of the answer, so I'm going to turn off my camera. Okay, so let's solve for acceleration. Acceleration equals gravity times mass 2 minus mass 1 over mass 1 plus mass 2 minus 1/2 mass, or of the mass of the pulley. Okay, and that's, I think I don't know if I mentioned that, but for the moment of inertia, the mass that we are using is the mass of the pulley and its radius. Alright, so, and lastly, acceleration can be less than or equal to gravity in this type of problem. Okay, so let's compare. We've got the Atwood machine versus rotation motion. We're using a pulley and we have 2 different masses. So first we need a diagram. This is the diagram of the Atwood machine. Pretty simple, pretty basic. Okay, it has no friction. Okay, we've got 2 tensions. Okay, 2 different masses, and there's both gravity acting upon them. Okay, now from the previous slide, I just used the same diagram. Okay, so here we can see a lot more information, and that's because we're using rotational motion. So we've got a few more things that we consider for this problem, which they're basically the same. You can see they're basically the same. Okay, we just got a little bit more information. So let's first figure out the sum of the forces for the Atwood machine, because that's really where we can compare them. Okay, so we've got force 1 times what is equal to the tension minus mass 1 times gravity, and that's equal to mass 1 times acceleration. Okay, so we can solve for tension. Okay, and I've done that here. It's just mass times gravity plus mass times acceleration. Okay, now we can solve for force 2, and that's using mass 2. So the tension minus mass 2 times gravity is equal to negative mass 2 times acceleration. Okay, just like with the other problem, we need to pick something to be negative. So solve for T, tension, and we've got mass times gravity minus mass times acceleration. Okay, see these are a little different. We've got adding and then we've got subtracting. Okay, so now we can set these equal to each other. That way we can solve for acceleration. So that's what I've done here. I just put, we've got mass 1, okay, and then is equal to mass 2, okay, with their gravity and acceleration. Now we want the acceleration and the gravities on same side, so that's what I did here. So mass 1 times acceleration plus mass 2 times acceleration is equal to mass 2 times gravity minus mass 1 times gravity. Okay, so now we can see using rotational motion, we use the sum of the forces, but we also use torques. Okay, so and I just brought over the problem that we used in the previous slide. Okay, so now we see some similarities here, but let's solve for acceleration so we can really see the difference in between the Atwood machine and rotation of motion. Okay, so solving for the acceleration, we've got the acceleration is equal to gravity times mass 2 minus mass 1 over mass 1 plus mass 2. Okay, so we solve for acceleration over here on this side, and we have pretty much the same thing. There's just one difference. Okay, and that is the we've got minus 1/2 times the mass of the pulley. Okay. Now, if you forgot what that is, that's just the moment of inertia. And we use that when we're dealing, we've got a specific shape. Okay, so what's the shape of a pulley? Well, it's a disc. Okay, so what do we consider when using rotation of motion? Because we've got a lot going on here compared to the Atwood machine. So we need to know the direction that the objects move. Okay, and that is when we use torque. Okay, if the direction is moving counterclockwise, it's positive. If it's moving clockwise, it's negative. Okay, and then we also need to consider the mass and radius of the pulley. And we use that in the moment of inertia. Well, to find the moment of inertia of something, we need to know the shape of the object. And that's the difference between the Atwood machine and using the rotation motion equations. Okay, so for discussion, my lab mates and I, we knew that the Atwood machine equation would be used. We found the moment of inertia equation, but we didn't know where that equation belonged. So what we did is we were able to find an example on the internet, and we were eventually given how to solve it. So we solved for acceleration. We weren't off. We had an idea. We didn't know exactly where. So we had help. And then in conclusion, I learned that including rotational motion of the pulley system will create a more accurate answer as opposed to using the Atwood machine. And then I also learned that the sum of torques and how the direction can affect the problem. My lab mates and I, we worked together to analyze a problem, and when one of us was stuck, the other was able to help or find an answer on the internet. So next time I will remember to consider torque and inertia when solving for these types of problems.